Okay, so I put this presentation together more to talk about theory behind electricity before we get into some of the solar car concepts. I think this is going to be, here's some knowledge for you and it'll have some practical applications as well. But you won't really understand a lot of this until you actually go and do stuff. And I know that Matt, before you left, had put together this test box of electrical stuff to explain concepts. And for those who are interested in pursuing more of this stuff, I can walk through that stuff with you guys. Okay. Okay. Our topics for today, I'm going to, like I said, go over some of the theory behind some of the electrical stuff, talking about wiring and instrumentation, and then we really get into the solar car portions in terms of the components, schematics, and then a few minor notes on electrical safety and troubleshooting. Okay, so that doesn't really, okay. So, most of you guys should already know the concepts of voltage, current, and resistance, right? But we may know those as just terms, but this way we can sort of visualize or understand what it actually is. A lot of times when we talk about electricity, we talk about the analogy of water flow. Okay, and so what happens is, in terms of voltage, it's really the difference in charge between 2 points, or otherwise we can also say it as the pressure, the difference, the pressure that's provided between 2 points. So if you look at this diagram, you could see that if I build this up to the top, it will have more pressure than down on the bottom. It's just, by gravity, a tank of water suspended up in the air, the more water you put in there, the more pressure you would have. That's what we're going to call voltage. Okay? I stole these graphics, I didn't make them, and so I will say that I really hate the term amperage as compared to current, but setting that aside, the thing is there. So when you look at current, it's basically the flow of that charge, right? So when you think about that in terms of water, it's the flow of water. Okay? So when you look at that, if you have a wider hose versus a thinner hose, which hose would get you more water flow? The wider, thicker one, right? And that's what this is trying to say, is that actually, given the same pressure. Okay, so if you have the same pressure right there, if you have a wider hose, or a thicker hose versus a thinner hose, you will get more current or less current based on that. Now, it's all about pressure. So if you decrease the amount of pressure by decreasing the amount of water, so there's less gravity happening, you could get to a point in which your thicker hose will actually transmit the same amount of water than you would a thinner hose with more pressure, right? That sort of makes sense, right? And so there is a relationship which we'll talk about on the next chart about the difference between voltage and current and resistance. Obviously, in a water flow example, when you have a smooth hose versus something with a kink, it will have more or less resistance. Okay? So does that make sense in terms of, for water, it's sort of like, oh, okay, that's pretty normal. We're just using that as an analogy. Okay, so there's a few things we need to understand in terms of using those concepts. The very first thing is you need to be able to have a complete circuit in order for the electrons flow. Electricity is just the concept of moving electrons from one place to another. Okay? And so in this case, a battery provides for a voltage across here in which when the circuit is complete, the electrons flow from the negative to positive side. Okay? So, when we say you have to complete a circuit, that's what this diagram is saying. It's saying that if you cut this, the switch is basically removing a portion of the circuit, there is no way that the positive and negative things are connected. So therefore, it's an open circuit, and that's what it's called. And so you need to have that complete circuit in order for electricity to flow. Makes sense. We already know this because we do this with the solar panel. Let me put some relationships up there for you. Ohm's law, V equals IR, voltage equals current. Current is I, not C for some reason, but voltage equals current times resistance. So the key thing we need to know about that and why it's useful for us is that if your current is constant, you can vary your voltage by resistance. So obviously, if I is constant, you divide R on both sides, I equals V over R, right? So if I wanted, for example, and we might have to do this for the zero, we have a 12-volt supplementary system, right? And we need to get to a 5-volt system for the potential, for the throttle, okay? The way you can do that because of Ohm's law is you can actually divide. You can put, like in here, 2 resistors, and this would be 12 volts there. And based off of the resistance that you have here, you can then adjust the output voltage. So the calculation is the output voltage is the resistance of this bottom part divided by the sum of this, basically percentage of this over that. And that's how you scale voltage. We'll have to do that. But Ohm's law is important to understand, and it sort of makes sense, right? So this is related to what we saw in the last chart in terms of you can vary your voltage or your resistance in order to get the same current. So if you think about it, we say that a water tank with lower pressure and a wider hose can have the same amount of current flow, water flow, as a high pressure, thinner, hose. So what does that mean in terms of resistance? Well, when you have a wider hose, you tend to have less resistance to the water flow, and if you have a thinner hose, you have more resistance. And so that's how these play together. The other thing is called Joule's first law, Q equals I squared RT. No one actually uses Q equals I squared RT. They just convert it to power, because we don't really care about heat, although I'll talk a little bit about heat and stuff. But the idea is power is current times voltage. Okay, and of course we care about that because everything we do is calculated in the amount of power that we have and how much we use and how much we put back in. And so you have to look and say, okay, given a particular voltage or current, you're going to have some amount of power draw or power, putting power back in. A note about heat. The Q equals I squared RT. I is of course current, resistance, R is resistance, and T equals time. The whole idea is that whenever you're transferring electricity, you will have some heat that is generated. That heat, if not properly contained, just gets lost into the environment as heat. If you have an improperly sized cable, for example, and you touch it and it's hot, you are basically losing electricity because of this Joule first. Okay, and so when we go around and we want to do optimizing, or if we have some issues that we're trying to figure out, you will say, okay, is there heat somewhere? Do I have issues with the? You shouldn't have that problem because you properly sized the cable in the first place. And we'll talk about that in a second. But the other thing about this power equation is, your power is obviously related to voltage and current, and so that means that you can increase voltage to decrease current. You can increase current, decrease voltage to increase current, increase voltage to decrease current to get the same amount of power. Okay, and so that's important because when you start specifying parts tend to operate at a particular voltage level, which means that if you choose a part that has high voltage, you will need to drive less current in it, and we'll talk about reasons why you might want to do that in the next chart. But if you run at lower voltage, then you might need higher current. Okay, the last concept that I'll talk about is series versus parallel. Okay, so series versus parallel just means that there are two ways of connecting components together. You can connect them together in line. Basically, you have a battery and all the components are in a line together. When you see this type of diagram, and you think of wires as a hose, what does that mean in terms of the volts? Let's go back and say, what does that mean for the current that runs in that loop? Is it more current? Let me ask this: the current that goes here versus the current that goes here versus that goes here, is that the same or different? Same, right? It's all one loop. There's no way for the current to go elsewhere, and so the current flow will just be the same throughout. So, given that, and given that the power, with Ohm's law, if the current stays the same here, and you have different resistance, drops here, what does that tell us about the voltage across those resistors? So let's give a more concrete example. If each resistor is the same, let's say each resistor is 5 ohms, and the battery is call it 30 volts, right? So what does that tell us about the voltage across each of the resistors? They add up. So what is the voltage across R1? voltage is 30, the resistors are all the same, you can call it 5 ohms, doesn't really matter. So what is the actual voltage across R1? The actual voltage across R1 would be 10 volts. Because you have 3 components, all sized the same, which means if the current is the same, you have to divide out the voltage, right, in order to get the same amount of voltage across. You said it's right. So the voltage adds up, right? So the voltage across R1 plus the voltage across R2 plus the voltage across R3 is the battery voltage. Okay, it has to be that way because the point here and the point here, when you think about the voltage, is the difference between in the energy between 2 points, right? So from this point to this point, you have a battery that's 30 volts, and so if you go across this way to here, that also has to be 30 volts. Which means that if you size these equally, then the voltage drop across each of these particular resistors would be 10. Obviously, that means that if I were to increase this to say that this is twice the resistance of these two things, and these are equal, then what happens with the voltage? The voltage across the battery is still 30 volts. What's the voltage across R1 versus the voltage across R2 and R3? Yes, the voltage across R1 would be twice that of R2 and R3. So in this case, you would have what we'll say, 2R plus R plus R. So total of 4R divided by, across 30 volts. So R is 7.5 volts, which means the voltage across R2 and R3 is 7.5 volts, which means the voltage across R1 is 15 volts. Okay? So again, the voltage divider type of thing. But the idea with series is that the voltage adds up. In our solar car, the place that is most prominent in terms of wiring things in series is the batteries. And well, batteries are actually wired in series parallel. We'll talk about that in a sec. But the thing that's wired in series is our solar panels. Each solar cell is wired in series, okay? Because each solar cell produces half a volt, and half a volt you can't do anything with. So you add a whole bunch of them together. If you look at our car, I think they're 4 by 8s. Is that what it is? 4 by 9, I believe. So there are 36 cells on a panel, and then that would give you, because you have to add up the voltage in terms of wired in series, 18 volts. Okay, so that's series. So when you think about parallel then, it means that you are connecting all of these up, and you're splitting components up. In this case, what happens to the current that the battery is providing? It increases. It stays the same. The battery's going to provide, and this is a good electrical component. The battery's going to provide whatever the load, the stuff that's connected to it, requires. Okay, and we'll talk more about that when we talk about shorts. But the idea is, given that the battery has a particular voltage, and given that it's connected to a particular load, which is in resistance, it will provide however much current it's going to need to drive it. It's sort of like once you plug it in, unless you have a way of adjusting it, it just plugs. Okay. Now, I guess the real question is, what happens to the current as it goes through the system? And what it is, you know, in this system, there's one hose. There's no forks off of it. The current just has to flow through that one hose. It doesn't get out. In this case, it's like you're starting to tee off different places where water can go, which means that the current sort of gets split up. Whatever the battery provides in terms of current, it gets split off across these resistors. Okay. Likewise, when we talk about voltage, right? What is the voltage across the resistors? They're the same, right? Because this point is the same as this point is the same as this point is the same as this point. This point is the same as this point, this point, this point. Which means the voltage across each of these resistors is the same as the batteries. Okay? So you divide your current across here, but your voltage stays the same. That's parallel circuit. So series, parallel. Okay. If the voltage across here is 30 volts, it's 30 volts all the way across. Okay, it's not 10 volts all the way across. But if we say that each resistor is 10 ohms,
Can we take the reciprocal or something? It's
reciprocal of what?
the ohms of resistance.
So I think when we're talking about current, you don't actually, well, and sure, you can take the reciprocal, but because it's you're saying I equals V over R, right? Is that why you're saying that? But basically, we're saying, you know, if this is 30 volts and this is 10 ohms, 10 ohms, 10 ohms, logically you go, okay, well, the resistance is going to be, the current's going to flow equally across that, and so it's going to be, you know, it's going to be 30 ohms over 30 volts, so you're going to get 1 amp across, you know, each of these, I believe. Well, oh, sorry, the resistance adds up, so that doesn't work. Let's see. If these are 10 ohms each.
If it's parallel, you don't have it.
Right, and you don't add up resistance. You have to divide across.
So the current doesn't?
Well, the current will be the same. If the resistance is the same here, the current to each of these is going to be the same. Okay? What that number is really what we're debating, because you essentially have to find the equivalent resistance because they're in parallel, and then so when you have actually they add up. The resistance should add up in that sense. Is that right? Let me see. No, it's the reciprocal. Yeah, it's parallel. It's different. Yes. So,
I remember learning about
right.
this.
So, if you have a circuit that goes, you know, what we have here, resistance, and the battery, and you want to convert that to the equivalent of this one resistance, you know, what is this resistance? So I believe that resistance is R1 plus R2 plus R3. And then you have to calculate back for it. I'm not going to do that here because, you know, but you get the concept that there's
all the same resistance.
the whole point is if it's the same resistance, you'll have the same current coming through here. So if you have, you know, more resistance on one versus, you know, another, then the concept that you need to understand is that current's going to flow to the least resistance. Spread over, right? If you have something that has no resistance, and then you have something that has resistance, then all the current will go through the no resistance path. If you have some resistance on one and more resistance on the other, it will be proportionally split, okay? So that's really the concept I wanted to show here. We can talk about the math in the future. Okay, batteries and battery capacity and power. We talked about the concept that power is voltage times current, okay? And actually that's the instantaneous power. And if you take that over time, then that's your capacity or your energy storage, okay? And one of the key things we need to understand is that if I gave you something that was 10 amp hours, that's a capacity of a battery, that means that typically that rating is that I can take 10 amps out of that battery in 1 hour. At least we're talking about lithium batteries in particular. Lead acid batteries are calculated differently. Lead acid batteries are calculated at 20-hour discharge rate. But anyway, at 1C is what we call it, is how much current does it take to discharge a battery in 1 hour. Now, if I were to discharge at 2C, so if I want to take the battery and I discharge at 20 amps instead of 10 amps, I do not get a half hour of runtime. Unfortunately, the battery chemistries is that the more that you take energy out of the battery, the less capacity it will have. Which also works in inverse, right? So if I were to take energy out at half an amp, or sorry, at 5 amps instead of 10 amps, I will likely get more than 2 hours worth of runtime out of that battery. Okay? This is why we really stress the idea of taking sips of power out of the car. If you spike the car full of energy, it's not that just that you use more energy. It also means that you've reduced the amount of capacity that we have. So you're actually using more power than you would if you were to spread that out over time. Okay? And so this is just a graph that shows you that your power tends to decrease as you increase the amount of C, or the amount of current that you take out of it. Okay? And if you look at it, the other thing about our batteries is lithium batteries, we're really trying not to get the batteries below 3 volts. It starts doing some real damage, and if below 2, they're dead. So, you have to look and say, well, okay, on a 3.0 voltage line, right there, we're saying, and this graph is not representative of the batteries we have. It's similar, but it's the points on the line is not necessarily what it is. So take that with a grain of salt. But we say that you really only get 88% of the capacity if you drive at 1C or 10 amps. And if you drove at 30 amps, you only get 55% of capacity. Okay, so you're really making it hard on yourself if you do that. Okay, now it gets back to your comment about the batteries being in series. The batteries are in series, but they are also in parallel. Okay, and the way that works is, well, actually, you tell me, how did we construct the battery pack? in terms of you had individual batteries, and what did we do with them?
Just holds it in the series.
So,
10 in parallel because basically we wired the positives together and the negatives together into a brick, right? What does that do when we put those 10 batteries together in parallel? What it increases the capacity and then keeps the voltage the same, right? Parallel keeps voltage the same, keeps and increases current. So you have 10 amp hour batteries. If you wire them in parallel, 10 of them together, you get 100 amp hours. Okay. Then we take these bricks and what do we do with them? We wire them in series. And so when we have a 3.2 volt nominal, and you wire them in series, how many times? 15. So how much voltage results?
48.
Exactly 48. 3.2 times 15. So that's how it is. It's your wire in series and wire in parallel. That's why we talk about wiring things in series, wiring things in parallel. You boost your voltage and current accordingly. Okay. And of course, that means that we have 48 volts at 100 amp hours, but like we said, we're not going to get 100 amp hours of actual capacity, right? So this is why I've been trying to push you guys to get to a place where you can run your car consistently so that we can go out there and drive at different speeds and find out what is your capacity, how much can you get out of the battery pack at whatever discharge rate that you have, so that when you're on the road, you'll have a chance to say, oh yes, I'm only going to have that much. Now you can do a paper exercise, right? You can say, well, I have data that tells me I'm discharging at this rate or that rate over, if I'm driving at 20 miles per hour, I'm going to draw, 25 amps or whatever the numbers are. And then you can get a graph like this for our battery in particular, and you could calculate for how much capacity you have. Might be a worthwhile exercise for those who have the time to do so. But we really want to also confirm that experimentally. Okay, that's all the things I have on sort of electrical concepts and what electricity is, electrical circuits are all about. Do you guys have any questions on that to start?
When you say ohms, what do you mean?
Ohms is the unit that we use to measure resistance. So voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. It's just the units that are used.
when something starts in parallel, does increase, but that's...
The amps increase.
So...
But power is amps over time, right? Current over time is your capacity.
Mm-hmm.
And so because your current increases, then your capacity increases.
Okay, so
Because it's over time. Right. Does that make sense? So if you have a battery, right? If you have a battery that is 10 amp hours, it means that you can discharge 10 amps over an hour, right? So given that current, increases and the voltage stays the same when you wire things in parallel, then if you have two batteries, you can then have 20 amps over that hour, 3 batteries, 30 amps over that hour, and so that's how you can add the capacity, because you say, well, 20 amps over an hour, 30 amps over an hour just means 20 amp hours and 30 amp hours. It's
Amp
the
hours is capacity, amps is the amount of current or amount of electrons.
right. So you can think of current as the instantaneous number, right? At any particular point in time, I'm going to discharge a certain amount of current. And then when you look over the period of time, so you are essentially integrating the samples of your currents over time, it will give you the amount of power that you use, sort of in amp hours. Actually, I'm actually using the wrong term. Power is in watts and watt hours. I'm just using the current capacity, which is in amp hour.
Wait, I have an analogy. So like current is basically speed, so miles per hour, and amp hours is basically distance, so mile. So if you went 60.
Yeah, so when you measure the amps, it would be less than your,
When you measure amps, what?
Yeah.
Keep going the thought, because everyone needs to understand. So
when you measure like the amps of your system at like some point in time, it should be less than amp hours.
no, not necessarily.
Amp hours is your gas tank.
Right. Amp
So
hours.
when you start pulling amps, you start at 0 and you go negative. So we have a 100 amp hour battery, right? So if we were to pull theoretically 100 amps on the battery, we will be able to drain the whole thing in 1 hour.
So if you went 2.
So in that analogy, what we're saying is that the battery is the gas tank, and the current is the flow of gas.
It means that if your amps is higher.
So let's go this way. Your batteries are 10 amp hours, right? Does that mean that you're limited to 10 amps? No, because that 10 amps would last you a whole hour. If I wanted to discharge it, instantaneously, and I stomp on the gas, I could get theoretically to 100 amps. I will not be running for a tenth of an hour or 6 minutes. For that, I'd probably run, 2 minutes or 1 minute, and then I'll be out. But the current could be larger than the capacity. It's just based on how long are you running that. Your question is, I had said something about I want us to run, on a track. I'm not saying on a track. I'm saying I want the car to continue to get out there and be tested so that it can run. And we typically run at a particular speed, right? So that we can get some data. But sorry, keep asking me the question.
You were saying something about like, if say we pull too much current, right? Does it lower the capacity of the batteries as well? Did you talk about something about that?
Yes.
It does.
So, like I said, if you had a 100% full battery, right, and you get out there and you run, and you discharge that 10 amp hour battery at 10 amps, you will get an hour just by that's the rating, right? But if I discharge it at 20 amps, I'm not going to get to run half an hour with that. It's not linear, right? So in that case, we need to find out, we can find out via the graph, how much capacity we actually have. By the way, also important to know, that capacity loss is not permanent, okay? It's just a battery chemistry thing, so it's just a temporary effect. It also works the other way, by the way. So, if you are charging back up, if you try to charge at at 10 amps, you should be able to charge at 1 hour. If you charge at 20 amps, it will probably take you a little less time to get, fully charged and so on, up to the peak conversion. the little other battery chemistry thing that says at the very top I can't force the rest of it in there. But anyway, so you have to adjust for that, and you have to say, typically we look at discharge, right? Because when we're driving, we drive with a net negative, right? We're going to draw both the solar array power and our battery power to drive the car. If you're stopped off the side of the road charging or in a rest stop, then it comes back up.
But when we're talking about, like, you know how you said the higher the draw, the lower the capacity?
Mhm.
So is it taking into account for the capacity, is it from our net or is it from our just
So what does, I'm going to ask questions instead of giving you answers. What does net represent when we
Solar.
measure net?
solar and the positive solar and the negative?
So what does that represent in relation to the battery? If I have a positive number,
That means we're getting more than what we
right, which means the battery is charging or discharging,
charging. Okay.
right?
So
And so net is all about its relationship to the battery. If it's a positive number, I'm charging. If it's a negative number, I'm discharging from the battery. Okay? So if I'm getting 10 amps coming in from solar, and I'm only using 8 amps, I'm positive 2 amps going into the battery, I'm charging. And so that's the effective charge or discharge rate. That's what net means. Okay, so if we're getting 15 amps of solar coming in, right, and we want to discharge at 1C in the battery, we actually can discharge at 25 amps, right? Because you're going to get 10 amps or 1C from the battery, and you're going to get 15 from the solar, and then you combine that together. Okay? And so that's really, so we sometimes when we do solar racing, we talk about driving solar only. Okay, and that's really saying whatever power I'm getting from the solar array, I'm just going to use that. I'm not going to take anything out of the battery. If we can do that, then the batteries don't discharge. We don't even have to worry about it. Or if we discharge just a small amount out of the batteries, we could get more capacity than we would, if we just drove battery alone. So, one of the things we need to look at is, sure, when we're driving out there, when we're driving out there, the key number we really care about is net minus solar. Because that tells you this is the amount of current we're actually driving to the motor, okay? And then you have to say, if I use that for every speed, I can plot how much current the motor needs, and if we can calculate how much power we get from the solar array, we can then estimate how much discharge we're going to take from the battery. If we just record the net number, doesn't mean anything, because on a sunny day you're going to have a better net number, and then on a cloudy day you're going to have a worse net number. You don't have all the information you need. You need both the net and the solar. Okay. Does that make sense? Okay. I don't know how much time I have, and I don't know what. It's already close to an hour, and I'm halfway through my presentation here. Do we have any urgent things we're trying to get?
No,
done?
we're here for, I think we're here to learn something here.
Okay.
And then whatever's left over, then we'll work on the project.
Okay. We'll keep going then. Okay. So wiring. Obviously, in the whole analogy of water and water pressure, we say that a thicker hose or a thinner hose gives you better water flow or worse water flow. And that's exactly the same thing with wire, right? A thicker wire allows the current to flow more easily, okay? And a thinner wire, because there's not so much conductors there, means that it will be harder to drive that current through, okay? So, now, if you have the same amount of power, and you change the voltage to a higher voltage, what do you get? You get lower current, okay? If you have lower current, it means that you could use a thinner wire because you don't have to drive as much current through the wire, okay? So this is the debate that people have had in solar car racing in terms of, do I want to run at, let's say, a 48 volt system that would be safer because you don't have a high voltage, but then it means that you need higher current, which also means that you need thicker wires, as compared to, you know, people who run at 72, 84, 96 volts. They can, you know, they can run at about half the current, which means that their wires can be thinner. Okay, it's a safety versus weight thing. In the past, we have tend to lean towards safety than the voltage, but at some point, certain motors just require certain voltage. For example, I think the Zero is running at what, a 72 or 96? I don't remember. Yeah, 72. So it's going to be higher voltage, which means your wires are going to be smaller. If you guys saw when the Zero was here, the wires that are run are smaller than the wires that we have.
Wait, do you want to explain what P equals R squared?
P equals IR squared.
Yeah.
P equals IR squared is just it's the same as P equals I.
Does that explain the higher the voltage, the less resistance you need, which means?
Well, P equals IR. That's or sorry, V equals IR. The Ohm's law, right? If you have the same, you're right. I know where you're going. So okay, P equals IV. I'm sorry, P equals IV, right? Power equals current times voltage, and then you're gonna say, let's say because V equals IR.
Oh yeah.
Right, that's where you're going.
R squared.
Then P equals I squared R.
Yeah.
Right? And so.
Does that help explain the higher voltage, or the voltage less resistance?
Not really. The P equals IV gives you that. Right? I mean, the idea is if you have the same power, at a higher voltage means you need less current. Okay? And then of course, if you do that, if you need less current, then you need less of a conductor to drive that. You're right, there's a resistance thing there in terms, but I squared R doesn't really tell you anything, right? The voltage is gone. you can't even calculate for it. But I mean, physics aside, conceptually you understand, right? That the thicker the wire, the more conductors there are in it, the easier the current flows through. Which means that you have to size your wire based on the capacity, or the amount of current that you expect to run through it. This is why in our drive wiring, you need thicker wire because you're going to drive a whole bunch of current to it. Whereas all our supplementary stuff, because they take 1 amp, half an amp, maybe the little fans take like 0.1 amp. They're really low current draw. You can use very thin wire. So on here, that's a double opt. So that's the thickest wire versus that's I think that says 18 gauge. For some reason, lower numbers means thicker wire, higher numbers means thinner wire. I don't know why you do that, but anyway. So for you to know and for scrutineering purposes, we use what gauge wire for our dry circuit? Yeah, I believe it's either 4 or 6. I'm trying to remember. I think it's 6. 6 gauge wire, and then we use something like 18 gauge, I think, for all our supplemental stuff, which actually Mary's walking over there to take a look. Yeah, of course. So we'll have to look, but you should know that because this is a similar table as what Matt had showed. It just looks different, but the idea is there are 2 things to consider in terms of sizing wire. One is the amount of current. What we said is the more current that you have to drive through it, the thicker the cable. But the second thing, interestingly enough, is distance. Does anyone have a guess as to why distance matters in terms of wire sizing? Will the voltage drop if it's longer? It shouldn't, but it does. The question is why. Just give a guess. You encounter more resistance. That's definitely one thing. And one thing is it encounters more resistance, and so but the thing is that we live in a practical world. In physics, everything is ideal. There are no losses anywhere, right? But in a practical world, there is leakage. Imagine you had a hose that you have to run a long distance, and imagine that there are little tiny holes poked into that hose as you go along. Things tend to leak out, and you go, well, how does it leak out? One is the increased resistance. The other is heat. Okay, we talked about how power and heat loss and things like that, it's just going to lose some stuff. Which means that the longer the wire, the thicker the wire needs to be, because the percentage of loss, if I poke the hole all the way through, the same size hole, into a thicker wire or a thinner wire, you're going to lose a smaller percentage of your current if you run thicker cable, just because your conductor is more than the holes that the losses that happen, right? And so when you size wire, you go and you can see that if I want to run 5 amps at 10 feet, I can run 16 gauge wire, but running at 50 feet, it's 10 wire gauge. So you need to see, and when we run things, especially when we look at the design of the new car, if you place things local to each other, you will have less electrical losses. Okay? Now, you also have to account for the mechanical portions of this in terms of, well, you can't put everything all in the same place because then it's a whole bunch of weight in one spot, especially if it's not symmetrical, then you're gonna have a leaning car, you have those type of things. But, and you're limited about where you can put things. But if you can localize your electrical components near each other, then you will have less losses. If you look at that car, we did that, right? Your batteries are in the back, right next to the motor controller, right next to the motor. So the wire runs are fairly local. The only thing that we have in there that's long is the disconnect switch. But by regulation, we have to have it in a place where the driver can access it and the exterior can access it, and therefore we have these long lines. Okay?
How does filter help with power?
So, if you have a wire that you're going to have a percentage of loss over the course of time, it's the same as like a hose run long distance and you have holes in them, right? If you have the same holes in it, when you have a bigger wire and a thinner wire, given the same pressure, right, given the same voltage, then you lose less. You will at any distance you will lose some amount of current. You're just gonna lose it to the environment. And so can you limit the percentage of loss?
Should we take a little break?
Yes. This is, well, let me run this and then we'll take a break. So the final thing about the wiring concept is short circuits and open circuits. We're already dealing with that in this car, but I just want to define the terminology, right? A short circuit means it bypasses the intended load or resistance. Okay, you want something to run through here in a certain way, but some reason you connected a wire from here to here, and so it creates a circuit that has nothing on it. It's just a wire. That's what's called a short circuit. And if the key thing is you know that the current's going to flow at the least your resistance, right? So if you just connect the wire, there's no resistance, which in a V equals IR concept, if you have resistance to be really low and your voltage, because your battery stays the same, what happens to your current? It goes infinitely high, which is why you get these arcs and sparks and stuff, because it's really high current to the point in which it actually goes across, so that's a short circuit. So you're bypassing the load, and so you're going to get current flow. How do you protect yourself against short circuits? Resistance. Yeah. Yes, resistance helps. But what we have in the car to protect against short circuits is a fuse. Because a fuse is intended to cut the circuit, to make a short circuit an open circuit, so that there's nothing connected, right? If you treat a fuse as a automatic switch, if I pop that switch open, there's no more circuit, right? So what a fuse does is, if a fuse detects that there is a certain amount of current that runs through it, it will blow, and then it will no longer have a circuit. Then that short circuit becomes open, and short circuits becoming open is a good thing, right? The short circuit is, you didn't want that in the first place, so then blow that to say, I don't want that circuit. Okay? So it will protect your components, because if you had a small resistor here and you had this LED that required a certain amount of current, and you drive it way too much, it's just going to blow that up. Instead, you could put that, if this was a fuse, for example, this would blow first, then no more current goes to there. That's how a short circuit. Open circuit is just the idea that you have a circuit that's incomplete, so you really want to intend to have a battery run this resistor and LED, but somehow something wasn't connected properly, and so there's no loop, there's no complete circuit that happens. And so you have to find those. In my troubleshooting section, we'll talk about how we discover or troubleshoot short circuits and open circuits. Okay. What would make it draw too much current? The resistance, right? So if you have a short circuit, or you have a resistance that's low, it's going to increase the current. Well, certain devices may not be able to handle that much current, right? Now, in a properly designed circuit, the way you connect things together, the devices say, well, I've got an internal resistance that I can handle. That's why the voltage is important, right? So this is why components have a voltage rating. It's like, I gotta drive the voltage to be 48 volts for our motor and motor controller. If I provide more than that, then because its internal resistance is a particular setting, then it could blow it could provide too much current than the motor controller or motor can handle. If you do too little, then you're not providing enough current to the motor and motor controller to do anything. So that's sort of why we tend to operate, things at a particular voltage level. Okay. Other questions? All right, break before I get into solar car components. I have